So hello all, welcome to Gate Methods. So today I am going to discuss that in a dynamic partitioning how operating system will keep track of the free spaces which are present in a main memory. Okay, how these free spaces are created. Suppose in a main memory we have 4 processes, and due to some reason either the process run to completion, or you can say it if it is completely executed by the CPU, or it has to go for a IO request, then it should be moved out from the main memory. And when it's moved out from the main memory, it will create a hole. Okay, and this process of moving in and moving out of a process will be very frequent. Okay, so how operating system will keep track of which part of a memory is free? So operating system mainly uses two methods to keep track of a free space in a main memory in dynamic memory allocation. Okay, dynamic partitioning you can say. So the first method we are going to discuss is bit mapping for dynamic partitioning. Okay, bit mapping for dynamic partitioning. For dynamic partitioning. So as we all know that memory is somewhat a single dimensional. Okay, for better understanding I have designed the diagram of a memory like this, but actually the memory is a single dimensional. It's a single dimensional run of bits where data is stored. And what we do in bit mapping, we divide our memory into some units. Okay, into some small units, and these units are known as allocation unit. Okay, these units are called as allocation unit. We divide this whole memory into some small units. Okay, small size units. So and the unit size, the allocation unit size is not to be taken too small, or it's not to be taken too large. Okay, and suppose we have taken the the size of each allocation unit as 4 byte. So here in a memory, this is a main memory, this is nothing but a main memory, and it is divided into some small that allocation unit. Okay, and the size of each allocation unit will be 4 byte, taken as 4 byte. Okay, and into that into a main memory, processes are stored. So we also have one array. Okay, what is array? It's a we also have an array which is going to represent that which part of a main memory is free and which part is allocated to the process. So it will represent, this array will represent one allocation unit. Okay, so this 1 bit cell of an array will represent one allocation unit. If the allocation unit is acquired by the process, okay, if these allocation unit are acquired by some process, suppose P1 is up till here, and this part of a memory is free because P2 is moved out, and this part is allocated to P3, P3, P3 and P3. Okay, so this 1 bit cell of an array will represent one allocation unit. Okay, so it will represent one allocation unit. If the corresponding allocation unit is acquired by some process, then we are going to store 1 in it in order to represent that it is acquired by some process. And if it is free, and if it is a hole in a memory, okay, if it is a free space in a memory, so we will be going to represent it by 0, 0, 0 and 0. So each cell in an array will store 1 bit of information, and it's going to represent one allocation unit in a memory. Okay, so how operating system will get to know that this part of a memory is free? By checking an array. If it got a run of zeros, a continuous run of zeros, then it will find out that this part of memory is free. So what's the problem in this method is, we are going to keep track of each 4 byte size allocation unit. So if the size of a memory is, let's say, 400 byte, okay, and we are dividing our 400 byte of memory. The total size of main memory, let's say, is 400 byte, and we are dividing our memory into some small 4 byte allocation unit. Okay, so 4 byte allocation unit. So how many allocation units are there in a main memory? There will be 100 allocation unit. Okay, so for 100 allocation unit, we are going to have a array of size 100. Okay, of size 100. So, and if we convert this 100 so of size 100 bit, okay, if we convert this 100 bit into a byte by dividing by 8, so it will come out to be something like 14 or 15. Okay, nearly 15. So the 15 byte of information, the 15 byte of space in the memory will be acquired by this array only. Okay, and this 15 byte of memory will be wasted because it is acquired by an array which is going to represent each allocation unit that we have divided in our memory into it. So this 15 byte will be going to waste. So what if we take the allocation the size of allocation unit as some larger value, like we will be taking this 4 bytes. Not to take a 4 byte, we will be taking, in place of taking a 4 byte, we will be taking it as 32 byte. Okay, so our each allocation unit will be of size 32 byte. So by taking let's say, not to take a 32 byte, we will be in place of 32 byte we will be taking 64 byte, let's say. Okay, so what's the problem in this? If we are taking some larger value of each allocation unit, if we are going to divide our memory into some larger allocation units, so the problem is, suppose each allocation unit is of 64 byte, 64 64 64. Okay, so our if our process is of let's say 320 bytes. Okay, so it will acquire 4 allocation unit. Our process of size 320 bytes will acquire 5 allocation unit. Okay, so let's say 5 allocation unit it will acquire. So there can be a possibility that our process will start from this half of the allocation unit and it's going to end till this half of the allocation unit. So half of the our process will start from here and will end up here. Okay, so it acquires half of that one allocation unit, half of that one allocation unit. So in array we are not going to represent as 0. In place of 0 we are going to represent as 1. Okay, so by taking a larger value, this half means the 32 byte here and 32 byte here is going to be wasted. Okay, total 64 byte is going to be wasted, and this is not for a single process. This can be this condition can be exist for all the processes. Okay, they are going to acquire half of the allocation unit, and in the array it will represent that it has acquired the full allocation unit. Okay, so this is a problem in bit mapping for dynamic partitioning, bit mapping method for dynamic partitioning. So in place of that, we are not using a bit mapping for dynamic partitioning. We are using a linked list in order to represent our memory. Okay, in order to represent our memory, we are not going to use bit mapping. In place of that, we are going to use a linked list method. Okay, what is there in a linked list method? So in a linked list method, we will not be going to have an array. In place of array, we will be going to have a linked list. Okay, for each process in the memory and for each hole in the memory, we are going to have a linked list. Okay, and this linked list has 3 parts. This part will contain the information if there is a process or if there is a hole in the memory, and this will going to store the starting address of that space and ending address. Okay, ending address. So if we represent this main memory that I have designed here, if we represent by using a linked list, then how we are going to represent it? So at first there is a process P1, so we simply write as P, and the starting address of the process is 100 and the ending address of the process is 350. Okay, and after that there is a hole, so we will be representing a hole by H, and the starting address of the hole is 350 and the ending address will be 500. Okay, and after that there is a process starting from location 500 and ending up in at address 600. And after that there is one hole. There is a hole which is created due to moving out of a process from the main memory. Hole is created, and the starting address is its starting address is 600 and the ending address is 950. Okay, so in this manner the linked list method is going to represent our memory, and the operating system will use this information in order to allocate process into the main memory. Okay, so this linked list is to be created in the increasing order of the starting address. Okay, we can place this 350 this 350 here also at first. Okay, but by storing this hole at front or before the first process, if we design that in that way that we are going to represent this part of memory at first. Okay, so what's the problem in that? If one more process leaves the main memory and creates a hole, then it will create problem in merging the two holes. Okay, if suppose if process P3 moves out of a memory, then it will create a hole. Okay, it will create a hole here. Hole will be created. So by storing this in the increasing order of starting address, we will be getting an advantage to merge these two. Okay, if we are storing in that way in increasing order of the starting address, then it will be helpful in merging the two holes. And if we are using doubly linked list also, then it will be helpful in merging two holes. So these two holes will be merged. Okay, what I am trying to say is, if the process P3 leaves out, okay, then these holes will be merged together. Okay, by creating a hole of bigger size of 250 byte. So if we are going to represent in this fashion, then we will be able to merge two holes. Okay, so that's all for now. In the next lecture we are going to discuss some methods in order to that are used to allocate memory to a process. Okay, we have that best fit, first fit, next fit and quick fit. These methods are used for both dynamic partitioning and fixed partitioning. So I'll be taking an example of dynamic partitioning, and by taking an example of dynamic partitioning, I will be going to explain you these 4 or 5 methods that are used to allocate memory to a process. Okay, thank you.